All right, so welcome back. I double checked to make sure that last video was audible and you could hear me, and I have to say it is not debatable. That is probably the greatest video on all of YouTube. That may be a biased opinion, but nevertheless, we must continue here. So there's really only one more step in this implicit differentiation process, and that's to actually solve for dy dx. So, but I tell you what, so instead of going through these four guidelines, let's hold off for just a second and let me start with what we know, okay? So remember these handouts, what you're looking at right now, this is the type of handouts that I give in class. And if you want to follow along, you can go to my website, which is just jeremiahdike.com. Once you're there, you look in the tabs where it says courses, find your course, and find this section. This is section 2.5. So, like I said, let's jump in. So you, what are we asked? So it says find dy dx given that y cubed plus y squared minus 5y minus x squared is equal to -4. Now, all right, first things first, forget about the title, forget about what's up here, all right? Notice that when it says find dy dx, it doesn't say find dy dx using the implicit differentiation process. No, it'll be your job to understand that you're going to have to use implicit differentiation. So, nevertheless, here we are. We want to find the derivative of the following. Let's see if I can adjust this a little bit better. Bear with me. There we go. Okay, so we want to find the derivative of the following function. Ready? So let's jump in. We're going to do exactly what we were doing prior. So the derivative of y cubed, we'll start with the left side of the equation. The derivative of y to the power of 3, since it's is going to be 3y squared. But since we took the derivative of y with respect to x, we have to have a dy dx. All right, so plus the derivative of y squared is simply 2y. Again, another dy dx must be attached. All right, the derivative of -5y is simply -5. But again, we took a derivative of a y variable with respect to an x variable, so we have to have a dy dx. Now, what about the derivative of -x squared? Well, this is just the normal types of derivatives that we've been taking all along. So the derivative of -x squared is simply -2x. Now, we have taken the derivative of the left side, but we also have to take the derivative of the right side. Now, so the derivative of -4 is 0. I'm going to pause. I'm going to pause for a second. Maybe what do I need to do to make sure you understand that what I'm about to tell you is a mistake that happens a lot? So how about this? I'll put a big star, and actually, yes, look at that. My star just totally did not work. That's because I changed the font size. Ready? Here's my star. Listen. So in my experience, and I've been teaching college math for a while, but in my experience, taking the derivative of the right side of the equation is the most often forgotten step. So students do very well taking the derivatives of the left side of the equations. They attach their dy dx's to all the y variables, but yet they go to the step that I'm at right now and they still have a -4 right here. Okay? So please don't do that. So now what do we do? Well, at this stage, what's going to happen is what we want, let's make sure we understand what we want. What we want in the end is a derivative, right? Oh my goodness, come on now. So what we want in the end is a derivative. We want dy dx equals. All right, well, right now we don't have dy dx isolated. So here's the step. anything that has a dy dx, any term that has a dy dx attached to it is going to stay on one side of the equation. Any term that does not have dy dx attached to it is going to go to the other side of the equation, right? So let's make sure you understand. Negative 2x does not have a dy dx attached to it, so this has to go to the other side of the equation, right? So let's rewrite this, and let me go do this quickly. So we got 3y squared dy dx plus 2y dy dx minus 5 dy dx. Now this is equal to, well, we brought the negative 2x to the right side of the equation, so it's equal to 2x. Okay. Now, let's consider this for a second. We want to solve for dy dx. So to do this, we're going to factor out a dy dx. Ready? So I want to factor out dy dx from every term on the left side of the equation. So let's see what's left. Well, this is going to be easy. This is going to be 3y squared is left here, plus 2y is left here, minus 5. Still equal to 2x. We did not change the right side of the equation. Okay, now, you are almost done. You're right there. The last step, if you want to solve for dy dx, is to simply divide both sides of this equation by whatever term attached to dy dx. So in this case, we're going to divide by 3y squared plus 2y minus 5. 3y squared plus 2y minus 5. At this stage, our terms cancel on the left side, leaving us with just dy dx. And look at the right side. So now what's left is 2x over 3y squared plus 2y minus 5. Now, you are done. This is the answer. But let's stay here for just a second. I want you to consider this derivative, right? Because this derivative looks a little bit different than the derivatives we've worked with prior. So notice that the derivative has both x variables as well as y variables in it. What does that mean? What does that mean for you? So hold on for a second. What is the purpose of a derivative? Well, remember, let's back up really quickly. The purpose of f of x is very simple. If you give me an x variable, then I will plug x into this original function and it will churn out a y variable, right? So if you were just simply interested in a height, or depending on how you have defined your variables, this is the correspondence here. You substitute x, so a value in for x, and out comes y. The derivative is different, right? The derivative is also a function. So normally, if you give me, if you have a derivative, normally what happens is if you give me an x value, I will plug it into my derivative, and what will come back out, is a slope, right? It's a slope of what? It's a slope of a tangent line to a curve. A slope of a line that is tangent to a curve at a point. And that is what we have here as well. So let me free up some space. So bear with me. So what I'm telling you is we have the same thing here. With this derivative, we have to give it an input because it is a function, but the output will also be the slope of a tangent line to a curve. But now look at what you would need to give me. You would need to give me both an x and a y variable. Maybe this will become clear. This is what we're going to do. So let's assume that the point 2, 0, and I don't know, let's say the point 1, -3 are on the graph of this function. Ready? We're going to go to Desmos. So now you're going to have to bear with me. I know you younger people know there's an easier way to do this, but let's see if I can. Okay, there we go. Hopefully it'll write. No, it doesn't write. It won't let me write on it. All right, well, so I'm going to have to go back, but at least I will get my point across with the graph. So now think about it. So what you're looking at here is the graph of the original function. Okay, now understand. Hold on for a second. I just thought of something. I told you this is going to be in real time. All the mistakes. What if I just go into Desmos? Can I write? No, I can't. What if I do this? What if I take a snapshot? And then I bring this up right here. What can I write now? Yes, look at me. Look at me. Okay, now relax. Just relax. I don't know what I'm doing. I'm old. So, all right, ready? So y cubed plus y squared minus 5y minus x squared equals -4, right? That is what you just got done doing, taking the derivative of, right? And what did we figure out the derivative was? Well, it was dy dx was equal to, I believe it was 2x over 3y squared plus 2y minus 5. I think that's right. All right. Now, remember, this is a function. The derivative is a function that generates a slope of a line tangent to a curve. Now, what is it that we want? Well, we want the slopes of the following 2 points. Okay? Let's start with this one. If you would like to know the slope on this curve at the point 1, -3, well, you would have to plug in 1 for x, and you would have to plug in -3 for y. So let's do that. Now we would have dy dx, the slope, is going to be equal to 2 multiplied by 1 over 3 multiplied by, now I'm plugging in, oh, look at me, I didn't plug in the negative, did I? -3, so x is 1, y is -3. So now let's plug in -3 for y. Okay, so plugging in -3. All right. Now, assuming that my arithmetic is correct, and that is not always the case, we should get, after everything is simplified, 1/8. So you can verify that on your own time. If there is some type of silly board mistake, then you can just laugh at me. No worries, okay? Everything, it's all good. So what did we just do? So, well, here's what we did. I'm going to try my best to draw the line that would run tangent to this curve. Oh, no. By the way, what I just did was with my finger, not the stylus. Those little green lines have nothing to do with this tutorial. So here's the line, the tangent line to the curve at the point 1, -3. What we figured out by plugging in, remember we plugged in x is 1 and y is -3, what we figured out is the slope of this tangent line is 1/8. Now obviously anything that is linear will retain the same slope throughout the entirety of the curve, right? Throughout the entirety of the line, and the line is just a curve. We now know that the slope of this point is 1/8. Okay? So let me see if I can get back to where I was. I hope that makes sense. Going through this process, I want to just delete the screenshot. I want to go back to my notes. All right, now where do we go from here? Well, we have a new skill. All we need to do is continue refining it. So now let me go through these 4 steps and let's see if it makes more sense. So if you want to, the guidelines, right? These basic guidelines for implicit differentiation. First, differentiate both sides of the equation with respect to x. That is what we began doing. Okay? Now, what we just got done learning for this tutorial is the next 3 steps. Collect all the terms involving dy dx on the left side of the equation and move all other terms, meaning the terms without dy dx, to the right side of the equation. Okay? Factor dy dx out of the left side of the equation and solve for dy dx. Done. Okay? This is your process. This is what you want to be able to do. Okay, so my apologies. We're going to go ahead and we're going to go to example 4. Okay. So it says, determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4. At the point, at the following point, the square root of 2, x is the square root of 2, y is -1 over the square root of 2. All right. So let's take a look. We want to start with the derivative. All right, the derivative with respect to x. So let's kind of pick up the pace a little bit. So we want to take the derivative with respect to x of x squared plus 4y squared is equal to 4. All right. So I'm going to, instead of changing colors often, we're going to stay in one color and go through this derivative. So let's begin. So the derivative of x squared with respect to x is simple. This is simply 2x. The derivative of 4y squared, again, with respect to x, is going to be, well, start with the derivative of 4y squared is 8y. And here's our dy dx. Okay, don't forget to take the derivative of the right side of the equation. So the derivative of a constant like 4 is just 0. Okay, step 1 of those 4 guidelines is done at this stage. Now, step 2 is to bring any terms with dy dx on the left side, any terms without dy dx to the right side. So this 2x is going to need to go to this side of the equation. Let's rewrite this. So now we have 8y dy dx is equal to, well, let's change the sign, so -2x. Okay, step 2 is done in those guidelines. Now, step 3 is not going to apply here. Remember, step 3 said factor out dy dx. Well, there's no need to factor out dy dx. right? Because I only have one dy dx. So I can move to step 4. Step 4 is to solve for dy dx, so let's do that now. Dividing both sides by 8y. That now tells me that my derivative dy dx is equal to negative 2x over 8y. All right, now, our only job here is just to clean this up a little bit. We have done all the heavy lifting. You have the derivative. Anything that you want can be derived from the function the way it sits. We just want a cleaner product. So we're going to simplify these fractions. So that leaves me with negative x over 4y. Okay, 2 goes into 8, 2 goes into 2. All right, now, if all that was requested of us was to find the derivative, we would be done. But that's not the case, right? They say, they come a little bit along a little bit farther, and they say, look, then find the slope of the tangent line at the following point. So we got to do that now. So the point that I'm going to erase everything except the derivative. So the point is going to be plugged into the derivative. So let me go ahead and do that now. All right, so I'm going to write this a little bit better. So the point under consideration is the square root of 2, comma, negative 1 over the square root of 2. All right, so let's do this. So we need to plug in the square root of 2 for x. We need to plug in negative 1 over the square root of 2 for y. And then we need to finish this guy up. So here we go. So the slope at the following point is going to be negative square root of 2 divided by 4 multiplied by negative 1 over the square root of 2. Okay. Now, the last thing to do is just to clean that up. Okay, don't get scared. All we have to do is flip our fractions, multiply our fractions, cancel anything that needs to be canceled, and we end up with 1/2 as our slope. Okay, so on your own time, you can walk through that math to make sure you can produce a slope of 1/2, but you are done. So what is the slope at that point on this curve? Well, it's 1/2. That's the rate of change. Ready? So let's do one more. So I saved example 5 is not as nice. So but let's jump right in. So we want to be able to take the derivative of, it says determine the slope of the graph of the following at the point 3, 1. Okay. Now, I'm going to probably have to, I don't have enough room here to finish this problem. So instead of just cluttering everything together, I'm probably going to bring up a new page. So bear with me. I'm going to, I don't know, check your phone, whatever it is that you are dying to do right now. And I'm going to see if I can find a, let's see if I can find a new page. Okay. So here we go. So I'm going to rewrite that question, and this gives me a lot more space. So the website that I was telling you about where those handouts are is at the top of this page. So ready? So let me rewrite it. It was 3x squared plus y squared squared is equal to 100xy. All right, so we want to be able to take the derivative of the following, and we were also interested in finding the slope at the point 3, 1. We'll get back to that. First, the derivative. So here we go. So let's take the derivative of this with respect to x. All right, now you have a choice. If you, that's not, looking at the left side of the equation, that's not too bad. You could FOIL all that out and make your derivative process easier. You could also run a chain on this, and that's actually what we're going to do right now. So it's just, again, just practicing skills. So in order to take the derivative of this left side of the equation, we're going to use, this is actually, so this is a chain rule. All right, so if we're going to use a chain rule, let's establish what it is that we want to define u to be. So in this case, u is going to be x squared plus y squared. All right, you know where we're going with this. Then we're going to need f of u. Well, that would mean plugging in u for x squared plus y squared, we would have 3u squared. Okay, now what else do we need? Well, we need f prime of u, and we need u prime. All right, starting with f prime of u. So the derivative of 3u squared is going to be 6u. Now, the derivative of u prime. So hold on, remember, the derivative of u prime is with respect to x. So we're going to need implicit differentiation here. So let's begin. So the derivative of x squared, well, that's easy. That's just 2x. And the derivative of y squared is going to be 2y, and here's our dy dx. Ready? Now let's establish the chain rule, f prime of u multiplied by u prime. We're now plugging everything in its right places. So f prime of u is going here. U prime is going here. All right, so that's, oh, what did I do? Nope. Okay, let me write that back. F prime of u. So here we go. So that's going to be 6u multiplied by 2x plus 2y dy dx. Okay, you know what has to happen. Your client gave you a function in terms of x's and y's. If you give them back a function in terms of u, your client doesn't quite understand what this variable here means. So let's get back to the formatting. So plugging in x squared plus y squared back in for u. So now we have 6 times x squared plus y squared times 2x plus 2y dy dx. There it is. Okay. Now, we are done with the derivative of the left side of the equation. Now, we're going to need the derivative of the right side of the equation. So I'm going to go ahead and do all the work that needs to be done right now. So now I want to take the derivative of the right side of the equation, which is 100 multiplied by x multiplied by y. Okay, so it is my hope that you notice that a chain rule is happening here. Apologies. A product rule is happening here. We have two variables that are two functions of variables, and we want the derivative of that product. So we're going to need a product rule. So let's begin. So we're going to take the derivative with respect to x. All right. Now the 100 plays no role in this derivative process. So I've just kind of trained myself to bring the 100 back out in front of the derivative. It doesn't matter. Okay, so in other words, what I'm going to do is I'm going to allow f to equal x. I'm going to allow g to equal y, then calculate f prime, calculate g prime. But what I'm trying to tell you is you could have placed a 100 here. It's no big deal. Okay, it's not going to affect our result. So let's finish it. So the derivative of doing f prime. So the derivative of x with respect to x is just 1. Now the derivative of y is, of course, dy dx. Beautiful. So now the product rule. So we have f prime times g plus f times g prime. Ready? The last thing to do is just put all of these pieces in the right place. So f prime we have defined to be 1. G is defined to be y. F is defined to be x. And g prime is, of course, dy dx. Now, at this stage, we're going to go ahead and get rid of all these parentheses that they're just cluttering things. So 1 times y is just y. And then x multiplied by dy dx is just simply x dy dx. Okay. So let me box in. And of course, let me not forget about my 100. Okay, so I've boxed in the results of taking the derivative of the left side of the equation, the right side of the equation. What I'm going to do now is give me some space. So I'm going to erase everything else. All right, let's go ahead and write the derivative. So the derivative of that function is 6 multiplied by x squared plus y squared multiplied by 2x plus 2y dy dx. Okay, and that is equal, so let me erase this, don't need this anymore, and that is equal to what? That is equal to, let's try that again, that is equal to 100 y plus 100 x dy dx. Okay, so now, if I have kept your attention that long, well, hats off, because that was a lot of work. I agree with you, but you have it. You have done that first step. Unfortunately, as in many things in calculus, anybody who teaches calculuses will tell you that the majority of the time, the hardest part of your calculus course is the algebra. So, in other words, I want you to take a look at what we have sitting here, and then understand that it would be your job to then solve for dy dx. Okay. Now, that is not, so none of this would be considered hard. I mean, this is training, algebra training that you have had ever since high school. But so it is tedious, but it's not hard. So you would have to slow down. You would have to. I'm not going to do this for you, by the way. This would take a little while. To just let you know, you'd have to distribute all of this out, foil all this out, get dy dx's on one side, everything else on the other side. So it would be a little bit of algebra work. But when all is said and done, you would get, and I'm going to write two different derivatives depending on if you reduce now or if you reduce during the stages of the algebra. So you would get, say, 100y minus 12x multiplied by x squared plus y squared over 12y multiplied by x squared plus y squared minus 100x. Now, so if you were not simplifying your fractions throughout the entirety of the problem, this would be probably what your result would look like. If you were to look up the solution, say, in the back of a book, instead it would look like this: 25y minus 3x times x squared plus y squared over negative 25x plus 3y times x squared plus y squared. Okay, so both are correct. You could graph them in, say, Desmos and confirm this. Both are correct in terms they are both the derivatives. Just one is a simplified form of the derivative. They've factored out and some like terms and canceled it. Now, again, I'm not trying to punt on all this work, but this is basically work that you already know how to do. So my job is to teach you the calculus. So after you have a derivative, the purpose of the derivative, well, the derivative is just a function that generates slopes at tangent lines at the points on the curves that you're interested in. So the last thing that you would have to do would be to use the point that was given, okay, which was 3, 1. You would have to plug x is equal to 3, y is equal to 1 into the derivative in order to get a slope. Okay, so if I plug in 3 for x, I plug in 1 for y. When all is said and done, 13 ninths is the slope. All right, we're going to conclude. Again, hats off. I know this has not been easy for you. And don't get me wrong, it's not easy for me either. I teach, you know me, at least some of you have had me for multiple semesters. I teach from pre-calc to differential equations, but I don't teach online. So I have to now try to figure out how to use some of this software. So again, I do appreciate your patience, and I hope this has been helpful. If you have any questions, feel free to email me. All the best.